Thank you very much for listening to this last presentation of this session. Indeed, I will walk you through the results we obtained with our optimization algorithms on a Coronaventilator. During the first wave of the pandemic, there was a worldwide fear that we would run out of ventilators to help patients breathing. And of course, engineers came up with novel ideas of quickly constructible and quickly designable ventilator systems to help and support patients breathing. Here in Flanders, two brothers of Ghent came up with their own design, and we quickly got in touch with them to support them in their design of the Coronaventilator. We could help them on two fronts, actually. By optimizing the design of the ventilator, we could reduce the amount of electrical energy needed to drive such a ventilator. This can be quite crucial in areas where 24/7 electricity supply is not guaranteed. On the other hand, by reducing the necessary torque to drive the mechanism, we can also reduce the cost of individual components. So here you can see the mechanism. You can see that a white indenter pushes or presses a yellow barge or back repetitively, and that's actually also the focus of our research. We heavily focus on the optimization of repetitive movements, and by using dedicated software, we can optimize the design, we can optimize the motion profile, we can optimize the selection of certain drivetrain parts, we can compare different studies, etc. There are many more other capabilities, but these four were covered in this research. So as you can see here, an often heavily overlooked optimization potential lies in the fact that the dimensions of certain rods, of certain elements, is not fixed a priori. You can mount the shafts on different locations. This is a mix-up between a 4-bar mechanism and a crank rod mechanism. And actually, the dimensions of all these shafts can be chosen differently. And we see that by choosing certain dimensions, we have a heavy impact on the actual torque necessary to drive the mechanism. Now, of course, we want to optimize the geometrical design, we want to optimize the mechanism, and therefore we want to stay as close as possible to the current state of use in the industry. And we see in the industry that machine constructors heavily rely on motion simulations, on 3D body, multi-body drawings in a certain CAD package. And we will depart from that CAD package, and the advantage is that certain parameters such as mass and inertia, flexibility are already automatically determined. That does not mean that the design engineer can leave everything up to the software. He also still needs to provide essential information on certain connections, the load, torque, friction, etc. I will skip this slide. To go immediately to the most important point is that here we have an optimization problem where we have exactly 3 design parameters. We can play with 3 lengths, and we also know the minimum and maximum of those lengths, so we also know the constraints on those design parameters. Now, what we want to do is actually quantifying the impact of changes in those design parameters on the actual objective, which is in this case the torque or the energy you need to drive the mechanism. And as stated before, we want to do this as close as possible to the current state of use in the industry, so we do not want to build up complex mathematical formulas. We want to rely completely on CAD software. We want to rely completely on 3D multi-body simulations. And we do that by initially testing if the design that is proposed by our optimization algorithm, if the combination of the 3 design parameters we chose is actually possible. Sometimes we can see on the left that it is not possible to mount these the rods with a certain length, or on the right that with certain parameters it is not possible to have the necessary indenter movement. Once we got rid of unfeasible designs, we have to do another simulation, because we define, or the users of the Coronaventilator define, that the indenter has to do a certain movement. But as you can see, the place where the indenter moves is not the place where we use a motor to drive the mechanism. So our first simulation here is used to do a kinematic analysis. Of course, you can do this in a mathematical and analytical way, but we use the full potential of our CAD package, so we use the fact that we can do this simulation to translate the necessary movement of the indenter to the necessary movement of the motor that drives the mechanism. Once we have done that, we can apply that position profile on the axis where the mechanism is driven, and we use our simulation, once again, yet another CAD simulation, to do a dynamic analysis and to reveal the actual torque you need to drive the mechanism. What we have done now is actually quite it's interesting, but we're not there yet because we only have one specific point in our design space now for one specific combination of the 3 design parameters. Now we can reveal the maximum torque we need or the root mean square torque we need to make that movement happen. And we needed 3 consecutive simulations for that, which approximately took us 3 minutes for the 3 simulations together. Now, of course, if we want to do a simulation, we have to reveal the impact of changes in our design parameter on that objective. And we can do that in a brute force way by, for instance, saying that we want a grid of 50 by 50 by 50 possibilities for each of our 3 design parameters. Then we would need 125,000 simulations, and this would take a very long time. So that's not possible. On the other hand, we're also not happy with such a coarse grid of 50 by 50 by 50 because we actually want to reveal the complete response surface to be able to exactly pinpoint the very best optimal design. In theoretical terms, this is called the global optimum. We actually want to see this, so we want in some way a formula describing the impact of each of the 3 design parameters. Here in this graph you only see 2 of them, just to make it more easy to illustrate this. But we want to reveal a mathematical formula describing the exact value of the objective based on the 3 design parameters. To do that, we heavily rely within our research on interpolation techniques, and especially in this case, sparse interpolation techniques. We also want to minimize the number of simulations you need to come up with that objective function. Finally, we were able to run a simulation, and we came up with all possible what we call sample points within the design space. And so in 9 hours, we were able to reveal that actually we could select a design of this Coronaventilator which had a root mean square torque which was about 44% less than the original design. So this means that we could reduce the energy needed to drive the mechanism by 44%. At the same time, we were able to reduce the maximum torque to drive this mechanism by 47%, which has a very big impact on the selection of your motor. You could actually choose a motor which is 47% smaller and also 47% cheaper. As I mentioned, we needed 9 hours to automatically run all these simulations. We were also lucky to be able to rely on software, like HEATS in this case, which automatically initiates the 3 different simulations. So what we saw in this project, it started about 2 years ago, that when we were at the start of this project, we also saw that many commercial providers started to come up with software like HEATS, which is able to automatically run different simulations in other simulation packages. So that was very nice for us because it confirmed our conviction that this approach is actually very relevant and quite innovative and can really make the difference in machine design. However, as I mentioned, 9 hours to come up with these results. It's nice, you can say 9 hours, you can easily do that overnight. Yes, but our ambition is that we could reduce these 9 hours by a factor 10, so that we can do this whole simulation, that we can do this whole optimization in a time that is less than 1 hour. Then this will allow machine designers, this will allow engineers to run multiple optimizations in one day, maybe alter with the concept a little bit, maybe playing with design parameters a little bit, run another simulation and get the result. We're on the right track to get there. We more and more rely on advances and breakthroughs in sparse interpolation techniques, which are actually able to absolutely minimize the number of simulations you need to do these optimizations. So in my last 10 seconds, I would like to thank the complete team, which is responsible for the results I presented today, and especially, of course, the brothers Steen and Jan Gerhots of Gear Up Medical, who were willing to collaborate with us.